Hello, everyone. Welcome to iCANX Talks. Actually, this was every Friday our group party, no matter where you are, early morning or later evening. So we met online and iCANX every Friday. So this is Alice. Warm welcome from Beijing. So I'm a moderator for this session. And very proud of that. This month we have super speakers from a different part of the universe. So Tian Li was from Shanghai, and Kim was from Seoul National University, and Keith was from Europe, Delft. So today we have Professor Long was from Tsinghua University, and today was our 201 sessions. So everyone knows that we're already here almost 4 or 5 years. So, and today's topic was quite interesting because today we first got to the quantum. So now many people also talk about quantum physics, quantum computing. Everything was looks like very close to our daily life. But today, Professor Long and this team going to tell us more details. So we're so happy to have young generations, on this stage. So I will introduce them one by one. First, let's welcome Professor Long to have his talk. Professor Long was from Tsinghua University. Actually, he's a very famous professor. And let me, try to find the best words how to introduce Professor Long because he won many honors, right? Yeah, prize, and as a super, scientist in academic. So Professor Long was a long time was working, in the quantum science and technology. Also have set up the center in Beijing and now be the deputy director, of Beijing Quantum Science and Technology Center. And he has, contributed to this field a lot. And also has his name named some algorithm, in quantum. So I think that's really not easy, but it must be very highlighted in this field. And he won a lot of awards. So I just want to announce a few of them. He won the second prize of National Natural Science Award. It also was a Rao Yutai Award of Chinese Physics Society, and internationally has IBM Global Faculty Award. So yeah, many of listed there. So I saved some time for Professor Long, to introduce his super nice work in this field. Professor Long, the stage is yours. Welcome.
Thank you very much, Alice, for the super introduction. Hello, everyone. I'm very pleased to share my work in this Friday, Super Friday. So the title of my talk is Whispering Using Quantum. I will give the talk in three parts. One, the introduction. We know in 1980, Benioff and Yuri Manin introduced the concept of quantum computing. In 1981, Feynman introduced the quantum simulation, and the idea was finalized by David Deutsch in 1985 for its universality, and now we know the Church-Turing principle. And I started the work in 1998. I did some work in the Grover algorithm. In the Grover algorithm, the original algorithm has some failure rate, and I replaces the phase inversion with phase rotation, and when the two phases equals this number, then the algorithm become exact. So this is called the quantum exact search algorithm, and some people call it the Grover-Long algorithm or Long algorithm. The breakthrough in quantum computing in 1994 and 96, Peter Shor gave the factorization algorithm. And so it is a big threat to the RSA, the asymmetric asymmetric cryptography algorithm. And Low Grover give the quantum search algorithm, which is square root to speed up the database search. Excuse me. And so the quantum computer are useful for anything involving computation, such as material search, crypto analysis, material design, and so on. And for instance, weather forecasting and so on. Traditionally, quantum computing uses the products of unitary. So here is the initial state, and we have a product. We have the product of unitaries, and this is the original one. And the Shor algorithm and the Grow algorithm all uses the product unitaries. And in 2002 and 2005, I introduced the linear combination of unitaries using this for quantum computation. And so these are the papers. And Stan Guder, a mathematician, showed that divided quantum computer can simulate any operator on a Hilbert space. And nowadays, the LCU has become linear combination of unitaries has become one of the 5 techniques for designing quantum algorithms. So, okay, I've skipped, and now come to the quantum computing threat to the RSA. And we know Shor algorithm kills the RSA, but it requires much larger quantum computer. For instance, to factorize 2048 integer, it requires 20 million qubits, and with 2 billion circuit depths. And the cutting edge techniques is from the IBM. It has 1,000 qubits and can perform 1,000 operations. So it is far less than that required for the task. And because it is a very important problem, and many people are working on that, in 2021, Peter Schnorr, a mathematician from Germany, proposed an algorithm using the shortest vector and to destroy RSA using classical computers. But the biggest problem, the biggest difficulty is to find the smooth pairs. And this is the Schnorr algorithm. Given an integer, first it designs a random lattice, then use, for instance, Barbie's algorithm to find the approximate closest vector, and then test the closest vector if it is a smooth pair. If it is a smooth pair, then we got it. When enough number of smooth pairs are collected, then we can solve a linear equation, linear set of linear equation to find the integer factors. But the difficult part is to find the smooth pair. And it has been shown that it is slower than the number sieve algorithm commonly used for factorization. And we, 24 researchers from 7 universities and research institutions in China, use this quantum computer, propose to use quantum computer to accelerate the finding of smooth pairs. And we factorized a 48 integer using only 10 qubits in a superconducting quantum computer, and set up a world record for factorization using real hardware, quantum hardware. the idea is to find the minimum of this factor. T is target, and this is the approximate solution. And then we vary around the solution. If this is the maximum, it is minimum. It closes to T. If this is 0, then this number is equals to the target. So in this way, when we find the eigenvalues of the Hamiltonian, the lower the eigenvalue, the shorter the corresponding vector, and so the more probable it produces a smooth pair. And this is the Hamiltonian. We can solve the eigenvalue problem using any quantum algorithm. For instance, QAOA or quantum annealing and so on. And we use the QAOA because we are using superconducting quantum computer. So this one is the Bobby solution. So it is not a smooth pair. But when we diagonalize the Hamiltonian,
as Professor Long mentioned before, quantum computing is becoming one of the promising area for researchers, also for like enterprise, because it presents a challenge to the limits of the Moore's law. So as we know that when the feature size of the silicon is about close to 1 nanometer, we facing the limitation of the Moore's law. On the other way, like the computing power is also of big demand in our life. For example, particularly recently, we call the large language model. It requires enormous like computing power. So how to solve this like dilemma in the next decade? We believe quantum computing is a promising solution to this problem. And as you see, it's rapidly advancing toward a future which will overcome supersede classical computing in a variety of applications. So quantum computing, the basic principle for quantum computing is the quantum parallel speed up. As we will say that in classical computing, we have n bits, but our memory can only store one state for this n bits. But in quantum computing, we have a superposition, which means that like in this table, a 4-bit memory will store 16 of the different possible states in a quantum memory. So in that way, if you do the quantum operation on this quantum memory, and we will achieve the speed up of 16 times compared to the classical computing. So this quantum computing provides a potentially exponential speed up on specific problem with huge information carrying an ultra-parallel processing capability unmatched by classical computing. So in this case, every national and nations will put quantum computing as a national strategy. For example, as Professor Long mentioned about our project, Chinese government has put a lot of plans and projects on quantum computing in the next decades, and also in the U.S., companies like IBM and Google, they have advanced much more in superconducting quantum computer, and the United States also have this the National Quantum Initiative Act in 2018, and in the Europe we'll see that company like in neutral atom like particle, they have now announced a partnership with Oil Giant and also partner with Saudi Arabia. So I think in quantum computing, this very we have a very fast pace to develop this new engine. So in quantum computing, like many of the market research present big market opportunities for this quantum computing in the future. And from the report in BCG, there are 4 aspects for quantum computing to have a huge market opportunity. So including like simulation, optimization, machine learning, and cryptography. I think Professor Long has mentioned about cryptography in his talk, and we will, for us, we are focusing on like simulation, optimization, and machine learning for the practical quantum computer to become going into the real world. So we developed I think in most of the applications, the parallel speed up will be most important, and also as a starting point is the optimization problem. So there are like this problem has application in like finance, insurance, and logics, and aerospace, and we will extend this algorithm and application into simulation and machine learning. We will show later. So let's talk about our technology. So we developed this coherent photonic quantum computer based on the optical quantum computing principle. So we describe a hard problem for Ising model. It's a mathematical model for like in physics and statistical mechanics, and it's very hard for the general Ising model to find a ground state, which is the minimum energy of given the expression shown on the left. And so we developed a new optical quantum computing way to store the spins into the like fiber memory, and we have each pulse is placed to simulate the spin up and spin down, and we're preparing the this optical pulse into a superposition of the spin up and spin down initially, and after the after we pumping the entire system, the quantum device will solve the optimization problem by finding the minimum loss of the entire system. And what we engineer is to map the Ising model, the Ising interaction by injecting the additional coherent optical pulse into the system. So in that case, the minimum weight of the minimum loss of the system will corresponding to the minimum energy to the Ising model. So additionally to compare to the to generate to work on the real problem, Ising model is not in fact enough, and in quantum computing area we also describe the problem as a quadratic constrained binary operation, is we called Kubo problem. So in that case, we have this our like software developed kit for SDK, and we can model the basic problem into a Kubo. We call Kubo model, and then we map to the Ising model and calculate in the machine of coherent photonic quantum computer, and we can find the best solution for this problem. So we have in Q-Boson, we have this hardware product And we have 550 computing qubits, which means that we can solve the problem up to 550 spins. And then in that case, using the Kanban speedup, we can find the best solution for this icing problem in milliseconds. And also, our optical quantum computing computer have a best like NTBF up to 12 hours, and we also support the private deployment. So the third part, we describe the use case we have made it in our company. So for the coherent photonic quantum computer, we believe is one of the most practical ways to make quantum computer into real world application. So we have this specialized quantum computer. By modeling the basic problem into the qubit problem. So we have like achievement to model this problem in finance and life science, and also artificial intelligence in and then we can be able to solve this problem using our hardware. So we will give some interesting application in next slide. So we have this application and also have a very great strategic partner in three areas. In finance, we have a partner with Ping An Bank, which one of the major bank in China, and we ran a feature screening problem in credit score on our hardware, and we have the results more than like 100 to 1,000 speed up in computing time and get a better result compared to the like classical computing. And also we partner with China Mobile, who is the biggest telecom giant in China. We have to optimizing the MIMO bin selection problem, so they can reduce cost and improve the service when for the mobile phones. And lastly, we also partner with Tsinghua University, with Professor Shengbo Li team. We propose using the icing model and qubit problem to train the quantized neural network and find the result. It has a potential to like train the neural network better and faster. The first example we will describe here is the CPQC application in AI. We have in traditional machine learning, we have the quantum classical algorithms solved on CPQC. So we can remodeling the clustering algorithm for community detection, which used in the traditional machine learning, like a Leuven algorithm. We developed the quantum community detection algorithm running on CPQC hardware, and the test result shows that we have better data separation capability against like classical algorithms. More importantly, we have a quantum algorithm to train the deep learning neural network. So as we show that we create a neural network to solve the MNIST data set, and we use the techniques such as binary constraint representation and also Rosenberg order reduction to model this network training problem into qubit problem. Then we have we can develop a training algorithm to this quantized feed-forward neural network trains on CPQC, and we achieve like 10 to 100 times speed up, and the result is comparable to classical computing. And also for the application in simulation. We have this like application in material science. So in material science, people want to go to create a material with several parameters to find like the best fit for the goal in the real application. For example, the transparency or also the like other aspect. So in our project here, we remodeling this like a fitting problem into the cubo model. So we have include several model several parameter into this spin up and spin down, and then we can use the classic we compare the classic computing and quantum computing running on CPU. We can see that we have better computation time and find a better solution, and the result shown on the right. We can see that we can find a solution with best fit with a real experiment. The last one is we have in the application in life science. So we have the CPU QC algorithm in molecular docking. The molecular docking is a very interesting problem. So in drug discovery and drug screening area, it's important to find a molecular which we call a ligand which best fit with the receptor in one best fit of the receptor. So we can model this best fit with the like binding energy to find a minimum binding energy for the ligand and the receptor. And we can use in the experiment like parameters to fit into our model, and then we can solve this cubo model using the on our CPQC hardware, and we can see the result has a very close fit of the ligand to the receptor, and has a but much shorter computation time. So this result has been published in JCPC, which is one of the top journal in chemical and life science. And this report, this result also interviewed by the reporter from Science. So finally, we have this application in finance, which is called portfolio optimization. So this problem is to find the best strategy to invest on several hundreds of shares, and given a risk factor. So this is a very classical cubo model, and we can solve this cubo model in our CPQC hardware, and we'll see that this is first time we can solve this problem on like 99 shares and have better and faster results compared to classical computing. And this result is also reported as given a national award in China. Yeah, and then we have a very interesting and promising application in practical quantum computing. So this is also our goal for QBoson in next decades. So our company started in 2020, and we are based on Beijing, and we have several rounds and finance, and this is our co-founders in QBoson. For me, I think Alex already introduced me, and also my partner COO in Ma, and my past. This is also our CTO, Dr. Wei. We are also from the top university in China and the US, and we believe much like interesting for us to develop practical quantum computing way and go to the real world application faster and faster than our other country and other like quantum computing path. So thank you for this is end of my talk. Thank you.
Okay, really looking forward for you, Q Bolson, to blooming. Yeah, so to be next generation, the big players in quantum computing. So yeah, thanks, Wen. Yeah, let's welcome our next speaker, and we're holding the questions till the end. Our next speaker is Professor Min Wang. So as Min was got his her PhD from Tsinghua University, actually, I supervisor should be Professor Long. So same group, and then she did a wonderful job, and then now she is a PI and Beijing Quantum Science Center. She won several awards, and he also did a wonderful job, published many papers. So Min, please share your slides. Okay, good. Yeah, we can see that.
Okay, is the slides good now?
Yeah, please. Okay, now,
Okay.
yeah,
Okay.
stage yours.
Hello, everyone. I'm Min Wang from Beijing Academy of Quantum Information Sciences. Before my talk, I want to thank the organizer, Alice, for organizing such a wonderful talk, platform, and also thank Professor Gui-Lu for the invitation and Dr. Wen for a very detailed introduction about quantum computation and quantum communication. Today, I want to talk about the progress of quantum network. I'm trying to answer the questions, what is a quantum network, why to build quantum networks, and how to build quantum networks. So quantum networks refer to the network using quantum entanglement resources to interconnect quantum information processing nodes, including quantum computing nodes, quantum communication nodes, and quantum sensing nodes. This interconnection enables coherent transmission of quantum state information among nodes, thereby providing functionalities such as secure quantum communication, distributed quantum computing, and distributed quantum sensing. There are two important reasons to build the quantum networks. First, is entanglement-assisted quantum networks can achieve large-scale quantum information processing. And second, entanglement-assisted quantum networks possess higher performance over classical network regarding to the security and also the channel capacity with entanglement. So if we build a quantum network, what components do we need? First, we need the quantum light source to generate single photons and entangled photon pairs. And second, we need quantum channel for with stable and compatible with existing devices. And third, we need quantum state detection for single or multi-qubit measurement. And also quantum memory for quantum repeater synchronization and feedback control. And fifth, the quantum processor for quantum information processing, error correction, entanglement purification, and quantum transduction. Here, this table gives a comprehensive composition between entanglement-assisted quantum networks and classical networks from the following 7 aspects, such as the physical resources, transmission method, transmission resources, transmission medium, relay solution, networking devices, and the protocol stack. For classical networks, we use deterministic signal characterized by macroscopic physical quantities, such as voltage and electric current. But for quantum networks, we need to use unknown quantum states characterized by macroscopic particles such as photons, cold atoms. And for classical networks, we have to follow the 3 steps: signal modulation, transmission through channel, and signal demodulation. For quantum networks, we should use quantum teleportation based on entanglement distribution and local operation and classical communication. For the transmission resources, classical networks use time, frequency, and spatial resources. And the quantum networks, besides the time, frequency, and spatial resources, we also use entanglement resources. And for the transmission medium, in classical networks, signals transmit in fiber, cable, free space. And for quantum networks, mainly the quantum states transmitted in fiber and free space. And also for relay solution, if we want to transmit for a longer distance, in classical networks, we benefit from the signal regeneration and amplification. But in quantum networks, we cannot do the signal regeneration and amplification. We have to use quantum repeaters based on quantum memory and entanglement swapping. And also for networking devices, in classical networks, we have hubs, routers, repeaters, switches. And in quantum networks, we need to use EPR source, quantum repeaters, and routers. And also for the protocol in classical networks, we have very mature protocols such as TCP, UDP, HTTP protocols. And also, but for the quantum networks, the protocols are still undergoing. So if we have all the above components, how to construct a quantum network? The first step involves constructing single quantum nodes, which can be categorized into two types based on their properties. The first type is the quantum operation node, also known as the quantum processors. Quantum processors can be realized on various physical platforms, including superconducting quantum systems, ion trap, optical system, atomic systems, and NV centers. Another type of quantum node is the quantum memory node, which is utilized for the storing of quantum states. With the quantum nodes, the next step to do is to connect the single quantum nodes to generate quantum entanglement among them, hence enabling coherent transfer of quantum information across nodes. The third step is constructing long-distance quantum network. The cornerstone of constructing long-distance quantum network lies in the distribution of long-range entanglement. We all know the quality of the entangled photons decay exponentially with increasing channel length. Consequently, currently the main approach for long-range entanglement distribution requires the use of quantum repeaters, within which quantum entanglement swapping enables the conversion of two short-range entanglements into a long-range entanglement. The fourth step is constructing long-distance multi-node quantum network. The next step is in constructing quantum networks involves the establishment of long-distance multi-node and quantum networks. And after we finish the first 4 steps, we can envision the building of fault-tolerant long-distance multi-node quantum networks. So to now, we have introduced the basic components and the construction process of building a quantum network. And in order to achieve this goal, we need to go step by step. In the year of 2018, a European group gave a roadmap for building a quantum network, which is divided into 6 stages, as we show it on the left screen, namely including the trusted repeater networks, prepare and measure networks, entanglement distribution networks, quantum memory networks, fault-tolerant few qubit networks, and quantum computing networks. Now we are in the first 3 stages. Because trusted repeater networks do not have end-to-end security, they cannot be used on a large scale. A practical quantum repeater will take more than 10 years to develop. So how to construct quantum network at this stage? In the year 2022, Professor Long and his collaborators proposed a 7-stage scheme for the construction of quantum networks, that is adding the secure repeater networks stage to the original roadmap. Secure repeater combines quantum secure direct communication, QSDC, with post-quantum cryptography, PQC. The post-cryptographic key encapsulation mechanism is used to encrypt the plain text, and the encrypted ciphertext is transferred using QSDC. PQC can provide computational security for nodes in the secure repeater networks, and QSDC offers quantum enhancement for classical networks. Thus, assisted by classical relay or classical repeater, we can build a quantum secure network with present-day technologies. The secure relay networks has end-to-end security, is compatible with internet, and also has the ability of eavesdropping perception and prevention, and also can be used together with the quantum relay networks in the future. This is a 3-node secure relay, secure repeater network prototype in our lab. We use the standard module lattice-based key encapsulation mechanism based on crystal Kyber algorithm to encrypt the plain text, and use quantum direct communication technology to transmit the ciphertext, and we achieve a time delay as short as 4 milliseconds at the relay node. MLCAM has a good balance of security, public and private key pair size, and computation speed. And the secure repeater network can provide node security for quantum networks, and also have quantum enhancement for classical networks. Besides the secure relay, secure repeater network, we use post-quantum cryptography to help quantum networks to have a longer transmission distance. We also need to use post cryptographic algorithms to realize the access authentication for large-scale quantum network. Recently, we propose an access authentication scheme for large-scale quantum communication network using the PQC KIME and the digital signature algorithm, Crystal Kyber and Crystal Dilithium. We construct access authentication protocols for quantum communication networks, including QKD network and QSDC networks, which have the security properties of mutual authentication, conditional anonymity, data confidentiality and integrity, and also unforgeability and undeniability. The paper is accepted by Science China Information Sciences recently. So, so the last page is for the outlook. In the future, we will connect the quantum communication systems, quantum synthesis systems, and quantum computers based on secure repeater, quantum repeater, intercity quantum network, space ground quantum network, and interstellar quantum network to build a global quantum network. and form a global quantum network with global secure communication, computing power recombination, and multiplication, and also quantum sensing capabilities. So this is my talk. Thank you for listening.
Okay, Min, really good talk, very clear, and all these informations are very important for us, like especially my name is Alice. So yeah, I'm so glad to see that Alice was on the quantum computing always, yeah, as an example. So very good. Yeah, let's go to our discussion. First, let me introduce our panelists. Today we are so lucky this popular quantum issue topics was attract more attentions. So we have two panelists. First is Professor Tiejun Wang. She is a professor in Beijing University of Post and Telecommunication University, and so she also served on the executive members of CCF for the quantum science of computing. And she also published a lot of papers and win, very super high level honors. So, Professor Wang, welcome. So, and our next, panelist is my young colleague in PK University, but he is in physics school, Peng Pai. Yeah, Peng Pai was graduate from PKU and then go to US for MIT and postdoc and Princeton. So it travel around and focus on quantum and photonics. So yeah, Pai, welcome you here. So let's welcome everyone get on the stage to start our panel discussion. So Peng Pai, maybe you go first for the questions, please.
Yes. Thanks a lot for inviting me here, and really glad to hear so many exciting results. So my first question would be for Professor Long. I'm particularly interested in the part that you make decoding RSA way easier using QAOA. And when the paper was out, I was still in the US. There was a lot of discussion, controversial there, and I'm really happy to hear the talk from you introducing all the details. So I guess the main remaining question toward that path is whether this advantage of the scale as we go classical bits goes longer and also qubits goes larger. So if we want to test that, what do you think would be the correct way to do it? Just do it using experiments, or there are other theory or numerical method that maybe can be faster than experiments?
Thank you, Pai, for the question. I'm glad you know the what was going on last year. Well, for your question, I think numerically it cannot be done on classical computer and supercomputers. So, if we, for instance, deal with a number, for instance, with 50 qubits, it will be very difficult for a classical computer to simulate or to calculate. So it had to be done in the real quantum computer. So I think it is one of the places, a few places that we can show quantum advantage in the future, especially I think at the moment. I think the goal may not be the deciphering RSA. I think it is too sensitive because it may be related to national security. I think a lot of comments last year are coming from the security people. I think academically we can treat it as how to say a benchmarking for quantum advantage. For instance, the RSA, we can test the capability of a quantum computer to say it can deciphering or factoring how many bits of number. I think it is real challenge. So, for instance, we can our work is we factorize the 48 Then someone come out, okay, we can factorize the 50 and so on. So in this way, I think we can we can see the can reach the quantum advantage in real problem. Okay, thank you.
Thanks. Follow up. So I remember that in your slides you show even for 2048 RSA 2048 only requires like 300 qubits, which is not like unrealistic number for now. So but I don't know, like there are other constraints that people cannot test it to larger scale at this moment, or just it's so sensitive that maybe people have already done and cannot release.
Thank you very much. I think, yeah, there are two numbers there. One is the number of qubits, and then the depth number. The depth number is I think 1,000. I think
Nice.
if translating the depth of the circuit, that is means 69 in quantum gates fidelity, 99 then dot 49 after dot percent. So I think the number of qubits we have realized the number of qubit level, but for the gate fidelity, there's still some way to go. Thank you.
Yes. Thanks.
Okay, yeah, Peng Pai, maybe we have our ladies. Yeah, so Tiejun, yeah.
Yes. Hello, everyone. Thank you very much for Alice's introduction. Thank you very much for the invitation of your team to come to the iCANX talks. Tonight my task is to ask a question. So I have some very simple, but maybe everyone was very most concerned about. The first question is for Dr. Wen. In addition to what have you said, can Dr. Wen also look forward to the future potential application of quantum computing in the field of artificial intelligence, AI? Dr. Wen.
Hi, Wen, you mute. Hi, Wen, you mute. Yeah.
Okay.
Oh, maybe.
Yeah. Thank you. So thanks for the question. I think so when I graduate from Stanford, I also aim to find the potential application for quantum computing. So I think my answer at that time is AI, and right now I think this answer is still hold. And as we are seeing, in last 10 years, in AI, particularly from the traditional machine learning to the large language model, the demand for the computing power scale up several magnitude. So I think I will believe that the quantum computing is one of the key solution to this computing power problem. And fortunately, we have some very good demo and application in this field. As I mentioned before, we have quantum clustering algorithm. We also train the deep learning network, although it's a very small scale, and we made it to train this binary neural network. I think they have shown the potential for quantum computing in the area of AI. So for me, in AI, most problem is also an optimization problem. So even for the linear regression problem, the way to do the linear regression is to optimize the parameter for the linear function to best fit of the experimental data. So this best fit we call the minimum is the square root of the mean root, I think. So to optimize the problem, and we also have a very small demo to run the linear regression on CPQC, and also have other application in algorithm like clustering and like k-means, which also find some like to finding the solution is to find the optimized point of this the model to best fit of the experiment data. And then come to the like neural networks area. I think the most interesting way for us is in like most content computing, like in most computer, we are very the best advantage for us is to solve the integer problem, especially the binary problem. So we first choose the binary neural network to do our first demo and application in training this neural network. And I think binary neural network and also other like bit 2 or bit 4 ink4 neural network, they have very good application in real world, because right now, even for the inference of this large language model, we still consume a lot of computing power and even the electricity power to do the inference. If we can like reduce the floating point network into this binary network, and we can very easy and have much lower power consumption for those like large model running on our hardware. So if we have demonstrated that using the quantum computer, particularly our CPQC, we can achieve to train a binary neural network which have same performance compared to classical algorithm, which is this is one of the key solution and key application of quantum computer in AI. In additional to this Kubo model, we know that they have other like we call the variational quantum algorithm called short for VQA, and this is like what Google and IBM they are doing. For example, TensorFlow content, they focus on training the content neural network using the parametric circuit, so content circuit. So I think this is a very hot topic, how to like using the quantum computer in the application of AI. So we believe we will find, and people will find a way, and which will bring a much more market opportunity to quantum computer in the next decade.
Okay, thank you very much. Thank you for your answers. I have a true understanding of the development and the cutting-edge research of the quantum computing. Sorry. But I still have a question that what is the most permission physical system for the quantum computing? Maybe your light computing or somewhere else?
I think there are several different aspects for quantum computers. So for us, like we work on the practical quantum computing, which we develop a special purpose quantum computer dedicated for this IC model and Kubo model for solving the optimization problems. I think also there's also other like famous like physical architecture to solve like optimization problem, like in superconducting computer, quantum computer, they have a quantum annealing, And also like what Professor Hai Peng has working on the neutral atom. I recently just learned that the neutral atom can solve this max independent set problem, which also is a NP-hard problem and for optimization problem. So I think in compared to what we said, universal quantum computers, those like dedicated or specialized purpose like quantum computer can have may have a first step to the real application, and then and also like in classic computer like GPU and CPU. So CPU can do the universal computing, but GPU that dedicate like in like matrix multiplication, and we have these two paths to like developing in parallel. And I think in even also similarly in quantum computing, like different hardware and different like quantum computers to solve different problems. They may like develop in the same time, and then we can in overall we can have a very we all have very big market like opportunity in the future.
Okay, thank you. I have another question for Dr. Wang. Dr. Wang.
Okay.
Yin.
Professor Wang, hi.
Hi. At this stage, is there any application of quantum network in use?
Okay, this is a very good question. Thank Professor Wang for this question. And for the quantum networks we talked about today, it is a quantum network combining quantum communication system, quantum computing systems, and quantum sensing system together. For this real quantum networks, we have not constructed yet. So I think there's no, it's like still academic research, so no practical applications. But now people heard a lot about the quantum communication network, and also China have done very good job. We have the trusted repeater network from Beijing to Shanghai, the quantum key distribution network, and also we have the quantum communication satellite. And also for QSDC, we have done some demonstration applications in banks and also in 5G special network with China Mobile Communications Corporation. And all these applications are, I think they are the demonstration applications. For quantum communication networks, the most important thing I think for now is to find the application scenarios to put forward the development of the technology. So I think go back to the questions, and for the quantum networks, there's no practical use, they are not in practical use yet, but for quantum communication networks, we have some demonstration applications already. Thank you for the question. Mm-hmm.
Okay, thank you very much. From the answer of Dr. Wang, I think that the quantum network is a huge system, and we should do much work for its application in the use.
Yeah, but we feel
Okay,
so excited because today we got Professor Long here. So I think quantum first in my mind, it must be a man's field. So yeah, but I feel so glad I see, so many super young scientists, female young scientists, very exciting. And also a lot of young generation was here. So very, very good. So, but I mean, yeah, I follow up that questions. So now they don't have a practical network, right, yet. So, but how long you think it will get into the real application? So how long takes years, 10 years, or 5 years, 3 years, or something? Yeah, so in your mind.
In my mind, I think it takes more than 10 years for real quantum networks. Yeah,
Okay,
because
I
we have to
see.
first we have to realize the general quantum computing systems, and also we have to use entanglement or quantum communication to connect all the systems like the computing nodes, the sensing nodes. So I think we have like 10 years or more.
Okay, I was thinking if we can enlarge the team, 10 times, maybe that will shot in, 3 years, possibly. Yeah. So, yeah, Professor Lu, that's a talk, why we want to, really got more people, moving in, especially in these hard topics, so exciting. But about really, really, I think 10 years, maybe 10 more years, got computing, quantum computing, all networks getting into reality. That's really exciting, already exciting, because yeah, so I think this was one kind. Now you are really struggling because you got a company, you got venture capital, because you visit one of my friends was invest money with you. He's really worried about that when he get money back. So yeah, please, okay, Kai, give us some your perspective for you, yeah, for you industry, yeah, for your company. So Kai, please, yeah. So you mute again, yeah.
Thanks, Alice. And this is a very good question. So first, I was when I first started the company, we also think about how the strategy to do a company as an entrepreneur rather than a researcher. And so we choose the way to do the practical quantum computer, which has a very which we can have a near-term like application in real world, and also we can have the technology to scale up much faster than other physical solution. And so that's why we choose this like CPQC or coherent photonic quantum computer, because it presents me we can scale up much better, much faster than other physical system, by sacrificing the universality of the quantum computer. So we are not like want to do a quantum computer to do everything, and we just want to have the one a quantum computer to solve one key problem. And we believe that optimization and also the AI is our goal. And which I mentioned that like GPU, and for GPU is the only one task it did is to do the matrix multiplication. And so we have this one quantum hardware to do one task, optimization much faster than other like a classical computer. And then we believe we can find a big market opportunity in very soon. But also thank you for our investor. They have investors. Most of them have the patience for this cutting edge like technology to go to the market.
Yeah, they pay for the future because now I'm thinking for the quantum computing maybe it's like 1970s, for the personal computing. So that time, everyone don't have the, personal computing, the PC, but still use a large one. Now the quantum computer maybe in the early stage like that. So yeah, they put the money in. Now it's $10, later will be millions. So that's what they fighting for. Yeah. So yeah, so we hope we can get more people, to put money in this field. I think that they will be more worse, Yeah. So very, very
Thank
nice.
you.
Yeah. So yeah, so glad to see all the young generation jumping in that field. So Professor Long, maybe I have a question for you. So I'm not really know how to do quantum computing, but I hear this so many times and it's already getting into the national level, right? Yeah, always everyone talk about competing this, competing that, But I'm thinking, so as you our Peng Pai, all these people have a very good international background. I also, collaborate with many of these, either in academia or in, industry. So I want you can tell us something about how the collaboration in the quantum field in the international level is. I think it's not just competing, it's also a lot of collaboration, right?
Thank you, Alice, for this very important and difficult question. And I think many of us in the communities think the current status come too early. I think quantum computing and quantum information as in general are still in the early stages of scientific research. But because there are too many expectations, so now it is always okay, at least in many occasions, reach to the level of national interest. So there are so many, embargoes and also the forbidden for the exchange of information. I think at least the mathematical parts and for instance the study of entanglement and so on, these and series, I think are still, I think we can still have free exchanges. But I think some technology, especially high technology, I think there's some okay, the difficulties in exporting or importing and so on. So I think as time goes, these problems can be solved naturally, hopefully. Thank you.
Yes, you're exactly right. Because just now I mentioned that, the quantum issues like 1970s for the, computers, right? The silicon based, all this
Right,
stuff.
you're
So
right.
that time, yeah, so it's early stage, everyone need to calibrate. Also academic was very active, then can put this moving forward, right? Yeah. So if I think about that time, we are maybe we are just jumping in the field and the 1970s. There will be plenty of the blue ocean, right? Yeah,
Yes,
the
yes.
blue oceans for all this. Yeah, so like Peng Pai, now you are in the right time, right? It's on time for your job. Yeah, yeah.
Yes,
So you
yes,
also,
exactly.
traveled, I think, in the several major players in this quantum the teams, right? Groups. So yeah, you just started your career. So what about you thinking, for the young generation or the young PIs can be, play in this quantum, field?
There are so many aspects in this field that are not fully explored. There are infinite opportunities, like from research, even on the as Tiejun has asked that there's a question of which platform is best, right? We don't even know. We all need to explore and prove ourselves. As now I have very specific targets from Professor Long that I need to make. 300 qubits with 6 9 gate fidelities, right? Everyone just work toward that with their own ways. And also, it's also very interesting to see there's enterprise companies coming, to really try to solve really near-term useful problems. And there are, I believe, more of that kind of problems to be explored. And yeah, I think and on a very long-term side, like Min has also been starting thinking of building a global quantum network, although even a local computational node hasn't been successfully built, but there are also long-term provisions. I think all of them are from bottom level to top level. There are infinite opportunities, and I feel like this is a very good time for me to join this very good field.
Yes, that's the best words I want to hear. So try to get more people moving in, Yeah, the plenty room, not only in the bottom, also in the top, right? Yeah, there's a lot of things to do here. So yeah, as time fly, today we really have a great discussion. So I'm thinking, yeah, maybe, like in silicon-based, all these issues we have, worse is more road, to follow, right? Yeah, so we'll target, every 2 years to double, triple all these things. Maybe in the quantum you'll have another law, right? Yeah, another law as like this driving the field going forward. We're looking forward to that. Yeah. Okay. Yeah. Let me time fly. Let me yeah. Thanks everyone for this wonderful talk. And yeah, it's time for me to do some job because at the very beginning, I tell everyone, if you answer the questions good, you will have the certification. I'm so proud that everyone not just answer the questions good. Yeah, it's simple. So Professor Long, thank you for your wonderful talk and your wonderful, perspective for this field and your contribution. Thank you very much. Yeah.
Thank
So I will
you.
send this by email to you. Okay. Yeah.
Thank
So
you.
yeah. Yeah. Taiwan. Yeah. So you have all this. Yeah. Please, put more efforts on the commercialization. We try to see that you're not only billionaires, but you're building the future. Yeah. Please. Yeah.
Thank you,
Okay.
Raj.
Min. Yeah. Min. Yeah, so proud of that,
Thank you.
young female scientist was, active in this field. Please, yeah, get more people, like you to, working in this hot topic and this future topic. Yeah, I really, really, excited about this. Yeah, and welcome.
Thank
I will
you.
send all this to, 3 of you and Qijun and Peng Pai. Yeah, be prepared, to get the online talk on iCANX. I'm really, really, try to host all the top scientists on this stage. So next week we're going to have another talk is for zinc oxide, the generators, and to the future. So the Professor Yamin Wang from France will be again on stage. We'll also have a big group, from different part of the world. We're going to have all these hot topics online. So see you next week and follow our iCANX, please. Thank you. Yeah, that's all for today.
Bye-bye.
Yeah.
Thank you.